There is a certain attraction to the idea that space is silent and still. It seems timeless and unchanging. The stars always seem to shine from the same place. And this sense of eternity may serve for some people as an anchor, a last resort, in a human world of unending chaos. But space is not like that at all. Rather, it is violent, ferocious, and lethal. It is fatally cold, and fatally hot, and seething with unimaginable energy that can fry you instantly. We are protected from this by a variety of factors that determine if we exist or not. That we can think about it at all is only because of the fundamental physical laws that determine if Earth is habitable or not. We in fact exist in a protective bubble, surrounded by, not to be too dramatic about it, violent, fatal horror. This violent, fatal horror is our own sun, which warms us, melts ice and snow in spring, and gives us lovely tans. But it can also kill us instantaneously. Our protective bubble is our magnetosphere and ionosphere. As scary as that may sound, this lovely star of ours gives us life and creates our weather and seasons, along with a number of other factors that are perfectly in balance to make our planet habitable. But what are the weather conditions like outside of Earth's atmosphere? Let's take a look. Space is full of stuff, and this is not just stars and galaxies and gas and dust. It is also full of radiation and the foam of virtual particles popping into and out of existence. It's busy out there. Voyager 1 has heard the hum of interstellar space. This hum is the gaseous plasma of space beyond the heliopause of our star, full of energetic particles. This is not technically what we call space weather, but the point is that nothing out there is peaceful or uneventful. Space weather consists of solar wind, coronal ejections, flares, cyclical and roughly predictable sunspots, and minor unexpected sunspots, and other phenomena of this sort. All stars create space weather, and sometimes it's quite dramatic. The effects of these can be significant, and as a result, it's important to understand what space weather is and how it occurs. This involves quite a lot of physics, specifically heliophysics, but the outlines are roughly explainable. Stars, including our Sun, may seem calm and constant to most of us, but they are not like this. They are in fact violent maelstroms of nuclear fusion, and the effects of this extend far beyond just heat and light, and even these familiar experiences may be deadly, depending on the star. But space weather is something altogether different. Every star has space weather, which may extend for billions of miles or kilometers from its photosphere, depending on the size and activity of the star. Around our Sun, this region is called the heliosphere, which is extremely asymmetrical and constantly changing in shape, due to the pressure of solar wind and the Sun's magnetic field. We hope you didn't get the idea that this would be simple. Consider the heliosphere. The heliosphere is a kind of bubble, caused by the Sun's emissions of energy, that extends far beyond the solar system. It's composed of several parts, the heliosphere proper, and several layers forming its outer edge. These include the termination shock, the Helios heath, a zone where the solar radiation has slowed to subsonic speeds, and then the heliopause, where the solar wind is stopped by the interstellar medium. Solar flares are short, individually unpredictable electromagnetic events that blast various types of electromagnetic radiation into space. They often form spectacular loops, because they are partially formed of ionized or electrically charged plasma from the Sun, which then follows magnetic field lines. Coronal mass ejections, or CMEs, are huge ejections of plasma and magnetic energy from the Sun's corona, carrying staggering amounts of energy at speeds up to 3,000 kilometers per second. They contain billions of tons of material from the corona and carry portions of the Sun's magnetic field. Solar flares and CMEs are often discussed together as solar eruptions. There are also coronal holes, which are areas that appear dark in extreme ultraviolet and X-rays, because they are cooler and less dense than surrounding hotter regions of the coronal plasma. The magnetic field in coronal holes is more open and unipolar, and as a result, these holes are the source of relatively fast streams of solar wind. The behaviour of our star can and does wreak havoc here on Earth, disrupting communications, power grids, Earth weather, satellites, and even the health and survival of astronauts, either on the ISS or beyond. It also causes the Van Allen belts, which are not a real danger to astronauts or probes, because these belts can be avoided, but which must be taken into account. Despite this, we're lucky, because our Sun, as a main sequence G-type star, is fairly placid as stars go. The most common type of star in our galaxy, and perhaps the universe, are red dwarfs, usually classed as M-type stars, although some classifications include K-type stars as well. In our own immediate neighbourhood, 50 of the 60 nearest stars are red dwarfs, such as Proxima Centauri. Proxima Centauri even has a planet that seems to occupy its habitable zone, although habitable may not be the best choice of words. The problem with red dwarfs is that they are generally long-lived, since their helium is continually remixed with hydrogen by convection, and therefore slow to be consumed in fusion reactions. They are also extremely unstable, and can flare up multiple times on a terrestrial Earth day. These flares spew out intense radiation. Proxima Centauri is one such very unstable star. Proxima Centauri is only 4.24 light-years away, but using current rather than fanciful technology, and using gravity assist, it would take 19,000 to 75,000 Earth-years to get there. But Proxima Centauri apparently has at least one planet, which seems to be in its habitable zone, and this sounds interesting. There might be some sort of life there, and this would be very interesting indeed. Unfortunately, this is also extremely unlikely, because Proxima Centauri is very highly unstable, blasting out withering amounts of various types of lethal radiation several times every Earth day. This paradoxically might jumpstart the initial appearance of life on Proxima Centauri, but these frequent, extraordinarily power blasts would also erode whatever atmosphere the planet may have developed, and as of now, we don't know if it actually has any atmosphere left, assuming it ever had one to begin with. As mentioned, the most well-known and familiar kinds of solar events that can cause us enormous problems are flares, coronal mass ejections, sunspots, and geomagnetic storms. Some of these events are correlated with mass communication failures and power grid failure. For example, the so-called Carrington event of 1859, a coronal mass ejection event, or CME, spontaneously lit up or burned out telegraph lines around the world. In March 1989, a huge CME brought down parts of Canada's power grid and melted some electrical transformers in the US state of New Jersey. In April of 2001, the most powerful flare ever recorded occurred, but we were lucky in that it wasn't directed towards us. If it had been, it would have resulted in worldwide communication and satellite failures. Near Halloween in 2003, a geomagnetic storm, caused by a solar flare, caused air travel to be rerouted, halted satellite communications, and caused a power failure in Sweden. Our magnetic field affords us considerable, but not complete, protection from most solar events. But this is not the case for satellites, and certainly wouldn't be true for any astronauts travelling through interplanetary space. Apollo astronauts were frankly very lucky that nothing major happened on the Sun during their trips to the Moon and back. Travellers to Mars and someday even beyond will almost certainly not be so lucky. Currently, aging and decentralised power grids are always vulnerable to flares and CMEs, and GPS positioning satellites are perpetually vulnerable to such events. Any crewed missions to Mars and beyond would absolutely have to carry shielding to protect the crews and instrumentation from frying as a result of a massive solar event. and this shielding would have to be considerably more robust than the shielding needed just to protect the crews and craft from ordinary background cosmic radiation. Perhaps not surprisingly, space weather is monitored continually, and there is, in the US, a division of the National Oceanic and Atmospheric Administration, or NOAA, called the Space Weather Prediction Center, and the National Centers for Environmental Information, or NCEI, which monitor and collate solar events to generate predictions, much as the Earth's weather is predicted or forecasted as far in advance as possible. As is well known, our own Sun has a partially predictable sunspot cycle of about 11 years duration. Sunspots are magnetic in origin, but we still do not fully understand the mechanisms. A recent study by the National Center for Atmospheric Research has suggested that there is actually a 22-year cycle with the 11-year cycle embedded in it. As technology becomes more sophisticated, it becomes more complex, and thus more vulnerable to unpredictability and even failures. What is clear is that since we can't alter our Sun's behaviour, we need to invest as much as we can in understanding and predicting this behaviour, so that we can plan around it. Certainly, shooting people into interplanetary space without knowing what conditions they may encounter is blindly reckless. Space is not a pleasant place. It isn't calm, peaceful, quiet, or benign. Rather, it is violent and deadly, including to all of us still remaining back here on Earth. If we think about how reliant we are on power grids, the internet, cell phones, GPS, and other such technologies, we should be rather worried about just how vulnerable these technologies actually are, and how at the mercy of our own star all of this spawning mess really is. We hope you've enjoyed this week's video. See you next time.